my name is Mike, and I'll be presenting today on the distribution of primes. So before we begin, I'd like to sort of address a couple of definitions. First of all, what is a prime number? A prime number is a positive integer that's only divisible by 1 in itself. Essentially, they're incredibly important in mathematics because they are the building blocks of the natural numbers. Every natural number has a unique prime factorization, and every combination of primes yields a unique integer. It's been known for a relatively long time that there are infinitely many primes. The basic Euclidean proof is to multiply all of the existing, if there are finitely many primes, to multiply all the existing primes and add 1. That new number, since it's not prime, it must be divisible by a prime that doesn't exist. And so hence we have a contradiction. But the thing about this proof is that, first of all, it's only like an indirect proof, and that it just shows that there cannot be finitely many primes. And the second thing is that it doesn't really tell us anything about the distribution of primes at all whatsoever. So in the 18th century, Euler sort of came up with another approach, noticing the series 1 over n to the s for all the natural numbers and some integer s, not integer, some real number s. We could sort of, assuming there are finitely many primes, we could rewrite this as a product of since every natural number has a unique prime factorization, we could rewrite this as a product of primes to some exponent. Of course, we could sort of factor this out. Since we have an infinite sum here, we could factor this as a product of multiple geometric series, each in the form of 1 to the p to the something power, which, using a geometric series formula, we could show that this is equal to the product of 1 minus 1 over each prime to the -1st power. If you notice, from calculus, we know that the sum of the series 1 over n diverges. So this sum on the left-hand side, if we take the limit as s approaches 1 from the right-hand side, it should go to infinity. But assuming there are finitely many primes, we know that 1 minus 1 over p is a non-zero term. So taking that to -1st power is a finite number. And since assuming there are finitely many primes, we'll have a finite product of finite numbers, which should be a finite number, not equal to infinity. Hence, we have a contradiction. Now, I guess, what does this really tell us? If we take the log of the right-hand side, we'll get a log of a product, which we could transform into a sum of logs of 1 minus 1 over p to the s. Using some Taylor expansions, we could sort of transform this into a sum of reciprocal primes plus some negligible terms. We know that from the last slide, the log of that product should diverge to infinity. So in essence, this here should also go to infinity, which implies that the reciprocal primes actually diverges. What does this really tell us? Well, first of all, I guess because we also know that, well, the sum of reciprocal squares actually converges. The sum of 1 over n squared from calculus converges. Because of that, primes in essence are more numerous or clustered than perfect squares. You could also say the same thing with any series that whose reciprocal converges, such as n times log n. And so from the second bullet, we could also sort of show that there are infinitely many integers x such that the number of primes less than or equal to x is greater than x over log squared x. So later on in the 19th century, Chebyshev creates 3 functions to sort of to help us understand the distribution of the primes. The first one is our standard pi of x counting function, which just counts how many primes are less than or equal to x. The second one is theta of x, which sums all of the log p for all primes less than or equal to x. And the third one is psi of x, which is equal to the sum of the Van Mogel function for all numbers less than or equal to x. The Van Mogel function is just equal to log p for all prime powers less than equal to x. In essence, it's theta of x, except for primes, it also works for prime powers. Of course, I guess, now that we have these 3 functions, how do we estimate them? Well, if you notice about the unique thing about logarithms is that logarithms, actually, if you exponentiate them, they become products. Sums become products. So if we exponentiate theta, we get e to the theta is actually equal to the product of all the primes that's equal to x. what are some next steps or approaches? Well, since we're talking about multiplication here, we could try to find things that divide each other. If some number a divides another number b, a is less than or equal to b, and to show that theta is linear, all we have to do is show that theta of 2n minus theta of n is equal to some linear term for all n. So I guess one thing we could first address is that all primes in between n and 2n for any integer n divide 2n choose n. This could be shown because the numerator of 2n choose n pretty much is 2n factorial, which contains all the primes in between n and 2n, but the denominator contains none of them, n factorial squared. And so that means that all the primes in between n and 2n must divide the numerator, since they're all still inside there. None of them get canceled out from the denominator. And in that sense, that means that, therefore, all the primes in between n and 2n, they divide 2n choose n, which is less than or equal to the sum of all 2n choose I, which is equal to 2 to the 2n from the binomial theorem. The product of all the primes in between n and 2n is equal to e to the 2 theta divided by e to the theta. So that has to be less than or equal to 2 to the 2n. And that, if we take the logarithm, we'll get theta of 2n minus theta of n is less than or equal to 2n times log 2. This here is a linear term, which means that theta of x is actually upper bounded by x. In a similar, well, not upper bounded by x, but upper bounded by x times some constant. In a similar way, we could sort of use the same approach to create a lower bound. And in fact, this shows that theta of x is asymptotically similar to x. How do we find, I guess, a bound for estimate for psi of x? Well, an interesting thing is we could try to look at psi of x in terms of theta of x. Take psi of x minus theta of x. This will equal here. If you notice something unique about this difference here, it's that for all primes whose square is greater than x, they will only have log p counted once, which means that it'll be canceled out by theta of x, all the log p's from theta of x. That essentially means to upper bound it, we actually only have to count the number of times log p will be counted for all primes less than or equal to square root of x. Because if p is greater than or equal to square root of x, its log p will only be counted once, and so therefore will be canceled out when we subtract from theta. Of course, the floor function is less than or equal to the number itself, and using this, we get some really nice cancellation that it's actually less than or equal to the sum of all primes that are less than or equal to square root of x of log x. Of course, this is the worst case if all numbers less than or equal to square root of x are prime, which means this is less than or equal to square root of x times log x. In essence, that means that psi of x is equal to theta of x plus big O of square root of x log x, which means that since theta of x is linear, it means psi of x is also linear because asymptotically similar to x, because this term is very small compared to the linear term. To find pi of x, our counting function, we need to introduce a new analytic tool, which is able summation by parts. This here looks like a little bit complex, but it's in fact just integration by parts in a more discrete manner. If we have a discrete function c and a differentiable function f, we could let capital C sort of be the discrete interval in a sense, just the sum of all c's. And we'll get this very neat formula here that we could use to simplify. And using this, well, it's not first very intuitive how we could find pi of x. But the interesting thing is that even though pi of x is only the sum of 1 for all primes less than or equal to x, we could sort of rewrite this as Cn times 1 over log n, where Cn is equal to log p if n is p and 0 otherwise. So that this sum here only really matters if for prime numbers. Using this, we could if you notice, Cn, because it's equal to log p, if n is equal to p or 0 otherwise, it's the sum of Cn is actually literally just theta of x, which means that if we plug in theta of x for c of x and 1 over log n for f of n, we'll actually get this is equal to theta of x over log x plus this integral here. And that integral could actually be sort of simplified because theta of t is asymptotically similar to t, this could actually be simplified to be upper bounded by some constant times x over log squared x. This takes some calculation here, so we're not going to go over it. But in fact, pi of x is equal to theta of x over log x plus big O of x over log squared x. This is really interesting because it really shows us, I guess, some type of interesting thing about the prime number theorem. The prime number theorem, if you guys don't know, it states that the counting function for primes is actually asymptotically equivalent to x over log x, which means that if we take the limit as x approaches infinity of pi x over x over log x, it should equal 1. And so because of what we found before, how theta of x is asymptotically equal to psi of x, which here we can also rewrite pi of x in a way. This shows that theta of x is the prime number theorem is equivalent to stating that theta of x is asymptotically equivalent to x, and psi of x is asymptotically equivalent to x. Why is this really important? Well, it's because if from previous slides, psi of x is actually equal to the sum of the Van Mogel function, which actually is very neatly related to the Riemann zeta function. This takes a little bit of work to compute, but it's a really beautiful thing here. And so using this, we could, using some other analytic tools such as Mellin transformations, Parent's formula, and contour integration, we could sort of find a bound for psi of x and show that it's actually the limit of psi of x divided by x is equal to 1 as x approaches infinity. So some interesting consequences of prime number theorem, some fun facts. If the prime number theorem is also related to something called the Mobius function, which it also states that if you pick a square-free number at random, the probability that it will have an even number of prime factors and an odd number of prime factors is actually equal. They're both half. And you could also sort of, interestingly enough, the error bound for psi x minus x, it's actually equivalent to, if you could sort of rewrite this as equivalent to the Riemann hypothesis, that psi x minus x is equal to big O of x to the half plus epsilon. For all epsilon is greater than 0, this is actually equivalent to Riemann hypothesis. So if anyone here wants to tackle that problem, you could also try proving this here. But yeah, that is the end of my presentation. I'd like to give a huge thanks to my mentor, Andrew, yes, for helping me go through all this. This was an incredibly fun journey. So.